Okay, great. So hi everyone, nice to meet you all. I'm Joheen. Yeah, I'm a first year grad student at MIT working with Aaron Kara, and I've also been collaborating with Ricardo and Jay on some new data that we have. So I have the fun task of getting to introduce all the basic observables behind QPEs. And that will hopefully help guide my discussions over the next couple of days. And I'll sort of note a disclaimer that these slides are mostly adapted from a contributed talk I recently gave at the HEAD conference in Hawaii. So you'll notice a slight bias towards one particular QPE candidate, but my goal really is to just give like a broad overview of the general phenomenology. So before I can sort of present why QPEs are so interesting and unique, I'll talk briefly about what we typically expect and see from AGN and the X-ray band. So in terms of photometry, we see stochastically varying light curves at 30 to 50% fractional variability. And the key is that this is almost always aperiodic and fairly random. And you can get a pretty large diversity of what AGN variability looks like, as you can even just see from the few I presented on the left. But yeah, aperiodic and random. And then spectrally, there are sort of a bunch of different components contributing to AGN X-ray spectra. And at soft X-rays, there's like a soft excess that you can typically model with a black body, but its nature is unclear. At harder X-rays, from 10 all the way up to 100 keV, there's the Compton reflection hub, but the dominant component really is this power law coming from typically attributed to the corona. And this is sort of much stronger than the other components contributing to AGN X-ray spectrum. So this extends all the way from soft up to hard X-rays. So then in 2019, when QPEs were discovered, courtesy of Giovanni, it was quite a surprise because they broke just about all of the rules that I mentioned in the previous slide. It's sort of remarkably ordered quasi-periodic bursts separated by an unusually sort of stable non-variable quiescence, and the spectral properties differ quite dramatically from typical AGN as well. So we now there's published in the literature 4 bona fide, well characterized QPE systems, and then 2 candidates that are starred there at the bottom. So the original source was GSN 69, which was initially followed up because it showed evidence for a TDE-like decay in X-rays that I'll talk more about in a few slides. Sources number 3 and 4 were found by Ricardo, who's going to tell you more about how he used Eurozeta to pick up these 2 very interesting sources, sort of giving us insight on the remarkable diversity of QPEs. And then sources number 2 and 5 were found by combing through the X-ray archives. So source number 2, RxJ1301, was found by Margherita Giustini shortly after the publication of the initial GSM 69 result. And it was found by basically considering what galaxies we knew of that shared these remarkably similar and unusual properties with GSM 69. So some of the unusual properties that GSM 69 showed were that it had a pretty small black hole mass of a few times 10 to the 5 solar masses. It was a super soft X-ray source, so there was very limited emission beyond 1 or 2 keV, and it was pretty much all thermal. And there were no broad optical or UV emission lines. So RxJ1301 shared all of these properties. There was one XMM archival observation of it from 2000 or 2001 shown at the top left there. And indeed, it showed this remarkable, unusual flare. So when it was followed up in 2019, it was confirmed as a true QPE candidate. And then source number 5, which we can only call a candidate because we weren't able to detect any sort of periodicity or that many flares from it, is shown at the bottom right here. And this was a project I undertook with Aaron back in 2021, where the idea was to comb the entire XMM archives algorithmically to see if we could find anything that looked like a QPE directly from just looking at the short-term light curve. So sort of free of the biases that may implicitly be present when you're looking for QPEs and similar sources to the ones you already know. So we caught 1.5 flares, and when we followed it up, the flaring had since stopped. So we can't really characterize very well the QPEs themselves in the system, but this source, as well as the recently published candidate that I'll tell you more about later, sort of can point suggestively towards different scenarios for the progenitors of these events. And to talk about sort of the relevant timescales and luminosities involved, the handful of QPEs that we now have typically recur on timescales of 2 to 20 hours and last about half an hour to, that should be like 10 to 15 hours, I think, is the flares of Euro QPE1. And then they typically peak at an X-ray luminosity of 10 to the 41 to all the way up to 10 to the 44. The recent one is quite bright. So you can really fill up an entire talk just with the complicated phenomenology associated with the properties of these flares. But as I was sort of alluding to earlier, one of the most interesting is the spectral properties of these QPEs. The main piece of interest is that the hard X-ray power law that we see coming from normal AGN is almost entirely absent. It's still there in the sources that we detect the quiescence, but very weak compared to usual. Instead, the dominant component is just a thermal black body emission. So on the bottom left, I have the spectral evolution of GSM 69, and in quiescence, which is the red, there's very soft black body slope, and this sort of smoothly varies up to a harder black body temperature of I think it's around 100 to 150 electron volts in this source. And then this smoothly varies back down as the flare sort of subsides. And this evolution is shown in the top right with, this is the flare profile itself, and then this is how the temperature varies along with that. And I should note that these don't go exactly in tandem. In fact, the temperature sort of peaks shortly before the luminosity does. And you can see this sort of more clearly in one of the Euro QPE sources, where the relationship between the luminosity and temperature is sort of more complicated than sort of going exactly hand in hand. But I expect there'll be more on this in Ricardo's stuff. And then just because I have the figure here already, see a similar dominant black body emission from GI249 as well. And since the QPEs disappeared between 2006 and 2021, we also saw a harder sort of spectral component emerge, sort of reminiscent of the more regular AGN power law. So something happened alongside the disappearance of QPEs between 2006 and 2021. If you look at the flares separated into different bands, you also get fairly different profiles. So the bottom left figure is the most relevant here. Because the quiescence is detected as a fairly soft black body, the peak amplitude at lower X-rays is going to be smaller than if you compare it to the harder bands where the quiescence is basically not detected. So the red, which is the softest band of 0.2 to 0.3 keV, has a smaller sort of characteristic amplitude than if you probe at harder bands. And in addition, the timing and duration properties are also strongly energy dependent. So at harder bands, you also get sort of narrower, more symmetric flares that also peak earlier. A couple other notes are that campaigns to sort of detect simultaneous variability at lower energies in optical, infrared, and radio haven't yet detected any simultaneous variability with the X-ray outbursts. But the caveat is that this is much harder to do because the photometry at those energies is more dominated by the host galaxies than X-rays will be. So my understanding is there's still sort of ongoing work on confirming this. And the lifetimes of QPEs have been, so the QPEs haven't permanently turned off in any of the confirmed sources since they were first detected in GSN 6.9 and both of the Erosita QPEs. The first chain of outbursts we saw came a few years ago, and they've all sort of continued flaring since then. RX 1301 has the longest sort of confirmed lifetime of QPEs so far, as we saw it flaring back in 2000, 2001. Earlier ROSAT observations from 1991 may have even caught part of a QPE flare. So the lifetime is at least 20, maybe even 30 years in that source. And we sort of know that it's less than 15 years in J0249. It's not clear when the flaring started, but it has to have turned off between the 15 years where we had observations. And then this is sort of one of the more interesting properties is that if you look sort of closely at the light curves, there's a pattern of alternating long, short recurrence times that also goes with high and low amplitudes. I think this is maybe easiest to see in the light curve of the 2019 light curve of RX 1301, where you have sort of a big flare followed by a long quiescence and then a small flare followed by a shorter quiescence. So my understanding is this sort of is one of the real motivators for pointing towards like an Embry scenario with an orbiting companion driving the QPEs. And this is seen in all of the sort of well-behaved sources. There's a loose scaling between the flare timescales and amplitudes. So the left plot shows the average QPE duration and how it scales with the recurrence time. So the sources where there's a longer time between the flares also tend to have the longest flares. The big outlier at the top right is 0 QPE1, which sort of is an outlier in many more ways than just this. And then there's also the amplitude, which is the peak emission divided by the quiescence, also seems to scale with these quantities. But interestingly, you might expect from typical variability, AGN variability, which in which the key parameter sort of determining the relevant, like that dominates in determining the relevant timescales is the black hole mass. There's not exactly a clear scaling with black hole mass of these timescales or luminosities. The most massive black hole showing QPEs is RX 1301, but it's sort of all the way down at the in the middle of the pack in terms of timescales. But another caveat I should add is that these are M sigma masses. So, and we're at the low end of the M sigma relation with these sources. So don't put too much faith. Okay, so the second part of my talk is going to focus on the observational connection that points very suggestively towards connection between TDEs and QPEs. So, like I had mentioned earlier, the initial interest in GSN 6.9 stemmed because it was an X-ray TDE candidate. At around 2010, it was detected with a flux like 200 times higher than previous ROSAT detections had placed it. And so this led to like a sort of years-long monitoring campaign to determine how the evolution of this TDE candidate would go. So this first long XMM observation was taken in 2014, I believe, and it showed this remarkably stable baseline, completely absent of typical AGN variability. And then as this monitoring campaign was continued to 2018 and 19, that's when these beautiful and surprising QPEs sort of emerged at near the end of the T to the minus 5/3 decay. And I should also mention that this characteristic power law decay slope isn't the only sort of evidence we have pointing towards the TDE in this source. A nice study of the HST UV spectrum from 2021 found that there's an abnormal carbon-nitrogen ratio in GSN 6.9, which is sort of generally associated with TDEs as well. In particular, it's like anomalously nitrogen-rich and carbon-poor, which I think points towards like a partial or complete disruption of a red giant sticker. Right. Okay. So the other sources, RX1301 and the two Rosita candidates, don't have the requisite sort of long-term X-ray coverage that we need to determine whether their baseline flux has changed significantly over many years. So we can't really say too much about whether there were TDEs in those sources. And then, like I mentioned earlier, we carried out a blind search of the whole XMM archive to try to find more QPE candidates. So this candidate was found from the light curve, from this short-term light curve directly. And then when we went and tried to find more archival information of it, it turned out that it was also a published TDE candidate, which was sort of surprising and interesting result. So at the time then, it was 2 out of the 5 QPE sources sort of associated somehow with a TDE. And I mean, TDEs themselves are already quite rare. QPEs are even rarer. So the likelihood that there's no sort of connection in the progenitors of these events becomes that much smaller when you consider that 40% of the sources have some sort of association. We saw the QPEs sort of halfway down the power law decay slope, and then when we followed it up in 2021, there was just this flat baseline, but again, reminiscent of the flat baseline of QPE sources when they're oh yeah, okay. And follow-up observations of GSN since the initial detection of QPEs have also found that they can turn off, and I'll let Giovanni talk more about these results in his talk tomorrow morning. Oh yes, and I just added this slide in, and just a few weeks ago, there was an interesting result that found the first QPE candidate associated with like the wake of an optical tidal disruption event. So my understanding is that it's sort of an unclear question whether different wavelengths at which TDEs are discovered sort of probe different populations of these sources. So it's interesting that we see that both X-ray and optical TDEs can lead to this sort of interesting X-ray flaring behavior. So this was like a ZTF TDE that peaked, it seems like in early 2020. And then about half a year later, some XMM follow-up found this half of a QPE like flare with sort of black body temperature consistent with what we see in the evolution of the other sources. But again, we can only call it a candidate because there's only been half a flare pictured in the bottom left there. Okay. So a study of the host galaxies of QPEs was led by Thomas Weavers in 2022, and DJ was also on that paper, so these are, direct your questions about this to him. And they found an overrepresentation of particularly rare types of galaxies that are also associated with the host galaxies of TDEs. So like I mentioned earlier, the M sigma masses find that these host galaxies are on the low end of supermassive black hole mass. And in addition to that, there seems to be a significant overrepresentation of QPE sources in this region of post-starburst galaxies. So low H alpha equivalent width, indicating little ongoing star formation, and then high absorption, indicating a recent starburst. So EuroQP1 and RX1301 both sort of sit in this very sparsely populated contour of the overall SDSS galaxy population. And yeah, this is a quite rare class of galaxies and is often associated with those galaxies of TDEs. So this is a big overrepresentation by a factor of like, I think 13 or something. But again, the caveat is that these are very small number statistics. So we really need to fan out the QPE population a little more before we can be sort of robustly convinced of this association. And one key difference is between the host galaxies of QPEs and TDEs is that if you put the QPE host galaxies on sort of a classic BPT diagram, they all have a clear ionizing source in excess of star formation. So they sit in this composite or AGN region of the BPT diagram. So they're not exactly the same as TDE host galaxies. So they might be TDEs in somewhat AGN-like environments, whatever that means.
Could this ionizing source be the QPE itself?
I don't know, maybe.
And what would it imply on the lifetime of this ionizing source?
I'm not really sure. An interesting point for discussion later, I guess. Okay. I'll quickly mention work that has been done on the models, but really that's, I mean, I feel like most of the people on these papers are like sitting in the room, so I'm not going to say too much. Early models focused on like maybe accretion disk instabilities as generating these QPEs. But then the really interesting thing about the 2 Zeta candidates is that they were found in galaxies without previously existing AGN. So that sort of disfavored that type of scenario. And it's also hard to sort of get some of the other characteristics, like the long short recurrence times with just pure accretion disk instabilities. So now most models are pointing towards some sort of orbital phenomena as driving QPEs, like an extreme mass ratio and spiral event with some stellar mass or smaller or greater than stellar mass companion in spiraling towards the central black hole. And then the prescription for how the emission is generated, whether it comes from interacting with the disk or direct accretion off of the source, or whatever sort of knobs you want to tune. That's the topic of sort of ongoing study. And I think that's an exciting sort of front that we can make some good progress on with the discussions in the next couple of days. Okay, great. So that's all I wanted to say. I have some key summary points up here. And yeah, thanks for listening. And I'm happy to take any questions as long as they're easy.
Yeah, great, thank you. Does anyone have any questions?
Yeah.
Fine.
One piece of phenomenology you didn't mention with the, and I think we're probably going to hear this later from Ricardo or Giovanni, is this claim that between the flares and GSN 069 that there's a QPO type signal from the quiescent source. Is that seen, and do we just not have the statistics for the other QPEs to actually say whether that's the case or not?
So the quiescence isn't detected well detected in the Eurozeta QPEs. And I don't think we see it in RX 1301, but that source is also quite irregular. So yeah.
So in general, we just don't see the quiescent emission in many of these sources. And how,
if it were detected in Euro QPE1, QPE2, which is sort of the other very well behaved candidate, that would be interesting.
Euro QPE2 is a bit absorbed and the signal noise is very low, and there aren't as many observations to perform this sort of analysis. RxJ's one is very highly irregular, so maybe you also require some sort of regularity in the bursts themselves to also have regularity in the continuum, if that makes sense. But yeah, we couldn't find any evidence of QPEs in the other sources, but mostly it was the quality of the data.
because there's a question of the QPEs, but then there's this also question as to whether, if we're not seeing the quiescent emission because it's being absorbed, or like how can we place constraints on the accretion rate of the black hole in these systems where we don't detect it? Like, are we? I guess it's just getting at the question of, in all these sources, is there actually an underlying quiescent accretion disk?
It's a hard question.
Or is it consistent with that? We can't prove it with these sources where we can't detect it. But I guess is there some level of accretion we could rule out? Like we could say these couldn't be accreting at Eddington or something.
Yeah, that's true. Yeah, I guess you could place good upper limits on how strongly they must be accreting.
It kind of comes back a little bit to Itai's question about, we see on larger scales that there's evidence for AGN activity. Like, is that my understanding is the narrow line region is quite far out. So in order to like power that, you have to have actually sustained accretion for very
Right.
long period of time relative to, say, a TDE or something, right?
The quiescence can be missed observationally. So in the soft X-rays, you see the peak, actually after the peak of the SD.
Yes.
So if you change this mass a little bit, you shift the SD, the lower energy. If you change the spin a little bit, and if you place it a little bit further out, it's a distance argument. So you can just miss the peak of the SD, but still most of the volumetric emission might come from this that we just don't see.
Right, so bolometrically, these systems could all be dominated by the quiescent
They are-
disk,
they
but it's just
are
so soft we can't see.
They are in the source that you see both quiescence and the QP spectrum, like at least comparable or greater, the volumetric of the disk emission. So just because we don't see the peak doesn't mean they don't have actually a strong ionizing continuum yet. How long it was there for, there's probably no way to say with this X-ray observation too. It's a topic for discussion.
Yeah, no, I just think it's important
No,
to
it's a good question.
understand.
Yeah, and
Yeah, so one thing I think is very interesting about the candidates so far is that they're all at relatively low redshift. They're all at, 0.01, 0.02, maybe 0.05, I think is the highest detection, at least of the initial 5 you showed. And so people are interested in this idea of the low black hole masses that tend to be associated with these objects. But I also worry a little bit about selection bias in that if for some reason you're sensitive to nearby detections and they're showing up in these low redshift sources, then statistically they're much more likely to be in dwarf galaxies, and that's going to imply a lower mass black hole. So I was wondering if people had perhaps thought about the degree to which that kind of statistical bias might be shunting the detections to lower black hole masses.
Yeah, fair. I think it's hard to say with such small number statistics. But it becomes tough because these are already sort of quite faint, difficult to detect. So I imagine at higher redshifts, that problem becomes even more sort of exacerbated. I know Ricardo's going to talk a bit about the rates and populations of QPEs that we can infer even just with the 5 or 6 sources so far. But yeah, I don't know, higher redshift QPEs would be great.
The two models you briefly mentioned near the end of your talk, MREs and disk instabilities, neither of those is directly connected to TDEs. So, I mean, are there TDE-based models? I mean, it seems, and also kind of, I guess, related question, if you have the last slide, it looks like they're kind of emerging, I guess, the one you were showing before, it looks like they emerge at late times. Before the near the this one, yeah. So if this figure is showing what you don't see it early in the curve and then they're showing up later,
Yeah.
you wonder maybe there's going to be a tail in a TDE that's raining down, till very late times,
Yes.
and you wonder maybe it takes some time for the beginning streams to turn into some structure, and it's the interaction with that late time tail with that structure that's causing it. Speculation.
Yeah, that's entirely possible.
But I guess an observational question is the fact that we don't see it until this late phase. Is that the fact that it wasn't present at that amplitude, or is it being outshined by, in other words, could they have been present even during the peak here, but it would have just been outshined by that secular quiescent?
Yeah, so a recent paper that Giovanni put out on results with GSN in terms of the evolution of how the QPEs weren't and were present in this sort of second reflare, I think will address many of those questions.
Yes, I think that was my recollection, was that it's basically being outshined by the quiescent. In other words, you could have had these flares earlier.
Right. So one result is that there must be sort of some coupling with the strength of the QPEs to the quiescent accretion rate. It's like the disappearance of QPEs here can't entirely be explained by, oh, there were flares going on at the same level as they were here, but now they're completely outshined. The flares must have gotten at least somewhat weaker
Okay.
in order to be completely absent in these.
So my point stands that that there has to be some, you have to have some reason why they're getting relatively brighter, I guess, during this briefing. I mean, to answer, can I just inject, because Mike raised this question of why connected to TDs, and I just want to very quickly answer. In our model, it's because for longer lived disks, they would destroy the QPE. So the reason we see them after TDs is because we need a transient source of gas, because if there's a star orbiting inside a long-lived AGN, it just won't survive. So the TD is just providing the gas disk, which lights up the QPEs. So it's sort of the causal connection is that a longer-lived AGN would have destroyed the star long before. But that, I'm sure there may be other explanations in other scenarios, but that's the connection.
A longer-lived AGN would have destroyed this star before it got down to these orbital periods.
Potentially, yes, or would have, yes, or destroyed, but at the very beginning creation of the AGN, I guess, which I guess is like what it maybe might also look like.
Also, to some extent, maybe in dwarf galaxies, feeding by TDs is not too unusual compared to normal AGN ignition.
Right, sure, yes, if there's a high fraction of gas accretions from TDs.
So would you see QPEs at like much longer orbital periods in existing AGN? If the disk is just much bigger, you don't get down to these short orbital periods, but you still see flares on like weeks to months or something?
So I mean, I'll talk about this model tomorrow, but you could imagine an analog of that where a star interacts with a more extended AGN disk. It's very unclear that this sort of interaction at larger radii would produce a phenomena that is similar to QPEs. So that is one thing to keep in mind, but just think of the periodicity, then yeah, there will be analogs of QPEs extending to greater periods. And I'll touch on that tomorrow, but maybe just to follow up on the discussion regarding the lack of QPEs at earlier phases during this TDE decay. I think we should also keep in mind that it's not just a question of being above the quiescence in terms of luminosity. There's also this gentle game of the temperature. Right, we're seeing essentially something that is like the wing tail of black body-like spectrum. So slight shifts. If QPEs, for instance, are slightly colder during earlier phases of this TDE decay, because the disk is evolving or whatnot, then that could also be part of the reason why we may or may not be able to see them. And there may be like the specific conditions in which this sort of interaction, this is very much model dependent, but this could also play an important role in setting the QPE detectability or observability. So just something to keep in mind.
Yeah, Martin.
First, question slightly off topic from what you have been discussing, but I was curious. I have to say I'm not an X-ray astronomer, just in case. But I remember, maybe 20 years ago, we had exquisite data from RxDE, timing properties of the X-ray sources. I know that was a millisecond dose, but I'm wondering whether on this, for the sources that have been observed for longer periods, anybody has gone and looked into whether there are these kind of phenomena already present.
So RxDE is a very small area covered by observation. It's a handful of extragalactic
So you have to actually point. That's the problem.
Yeah, but it's well, regardless of that, unless by chance they were observing this particular HC3 galaxy before, for whatever reason, there wouldn't be anything in the archive. But to be fair, nobody checked the thing.
I don't remember. I mean, certainly there were a lot of C3 galaxies looked at. I don't remember the numbers, but people were actually looking at, precisely timing properties in X-rays of these sources.
My guess would be that since RxD for extragalactic objects was used to study the variability of AGN, you wanted to point it at something that was knowingly bright and a known object, and these weren't. So I'm guessing either it was there by chance in the field of view sometime. I don't think it was observed, but somebody should check.
Yeah, so XT was greater than 3 keV, and none of these have anything.
Oh, that's a good point, actually, yeah.
I'm sorry, can you repeat that?
XT operated in a hard X-ray band,
Yeah,
so that's
okay,
greater than 3 keV.
yes,
So none of these QPE sources have anything above like 2 keV.
sure, but now that you know the phenomena exists, is there something preventing this from showing up at higher frequency, higher energies? There could be an analogous of this at higher.
So one, they have to show up at higher energies, and two, they have to operate on different time scale. So all of these are like less than a week time scale, right? The XT ASM had this all sky monitor that was very shallow, one thing, right? 10 to the minus 13, 12, something really shallow. So it's not that deep, the ASM. You have beautiful light curves from ASM for several hundreds of targets, like that data is public. One can go look at the light curves of all the known AGN. And I mean, nothing like this, obviously, because they don't show up in the light curves.
But looking to all the archives and finding more QPEs, it's a topic of discussion for later, so we can keep discussing on this, yeah.
We're also going back to Itai's point about timescales, right? So if they're further out, the timescale should be longer, but it's not just the timescales, but further out, the disk is emitting in optical.
Right.
Right, so maybe not X-rays, right?
Yeah, that was what I was alluding to, that possibly, these sort of interactions would look very different from these QPEs, and it wouldn't necessarily be in X-rays. The flare duration and energetics, it would all be different. So if we do end up seeing something similar in any other band with some sort of periodicity, it'd be interesting to think about the possible connection to
So we have Assassin 14KL, the one Anna,
Right.
is Anna here? Anna Ping?
Yeah, you're right.
Okay. The mask. Okay, so I guess are you gonna talk about it?
Yeah, on Wednesday, yeah.
So I guess we'll hear all about the optical, like QPE, whatever you want to call it, source. But also going back to Brian's point about why do you not see it in the early times? If you go back to your model, the idea is, I guess, MRE plus TDE, right? So initially, you need a certain amount of time for that material to come closer in. The TDE material to come closer in, the circularization process, or what you're going to call it. So unless you get that material in, it's not able to illuminate the presence of the secondary object, right?
Yeah, so if you think during this peak of the X-rays that we have, it's still some kind of like shocks and it's still some kind of mess and it hasn't formed a disk, then yeah, you could say the disk hasn't formed at that point. Or I mean, also as Itai said, the disk properties are changing, and a star breaking out of a disk, I mean, it's going to produce different emission when that accretion rate is higher at the early part of the TD. The disk is thicker and there's less differentiation, but it's less this sort of thin, clean structure that a star breaking out of. But I guess I was going to ask, with regards to, there is actual optical data on these guys to say they're not optically bright TDs, or we just don't know?
There is, right?
There is. So you can exclude that they were optically bright.
But the photometry in the optical and UV that comes for free with XLM has been the same for the last maybe 12, 15 years. It's been compatible. So that didn't really change much. But I don't think there is, some of this beautiful like cadence optical light curve simultaneously.
That's like fairly commonly seen, right? In optical and X-ray TDs, they're usually not TDs, and if you see one in optical, it's usually not a TD in X-rays, and vice versa. So
There's a lag.
there's a lag.
Also, I don't know if anybody has looked in Assassin data of the QPEs. I did maybe a while back and I didn't find anything. I don't know if somebody looked more carefully. Do you know?
Yeah, no, I'm involved in that work and there's not really been too much, but it's kind of like early stages. But I'll touch on that on Wednesday.
Okay, nice.
And just one last question before we move on. So you mentioned that you did like systematic search for QPEs in the XMM archive.
Yeah.
Was there would you comment more on that? And was there like an upper limit on the burst duration timescale that you'd be sensitive to? So like if there was, say for example, QPEs with durations of maybe 48 hours, would we have been sensitive to them with this search?
No, so the way I did the search was with an algorithm. It's it was originally devised to find exoplanet transits with transit timing variations. So it's called quasi-periodic automated transit search. But it turns out that if you turn an exoplanet transit upside down, it so I just ran that on all of the sort of short-term light curves, and kept any candidates that showed like more than one of these flares without any restriction on it. So the timescales are actually going to be set by the durations of the observations themselves.
But like I say, if we've got a source where you've got multiple observations over the duration of X.
Yeah, I actually didn't. I just ran on the individual one.
Okay.
Yeah,
So it might be something cool to look into.
yeah, definitely.
It might be a lot of work. But
The group from Toulouse, from Erwin, the one they found the candidate,
right.
They ran their own algorithm without requiring periodicity. And there was a paper that applied machine learning to the archive to it's pretty much three independent works, and they found two candidates. So
Okay.
it's true that for instance, the machine learning didn't trigger on your QPE1.
Yeah.
So yes, there is probably maybe room for something to be found at the edges of the parameter space brought by this algorithm, but the more obvious candidates are probably found, I guess. Yeah.
Okay. Yeah, I suggest if we have any more questions for Joheen, then put them on the Slack channel and we can come back to them this afternoon on a coffee break. For now, yeah, let's thank Joheen once more.